Welcome to this explainer. Right now, completely under our noses, a massive structural shift is happening in heavy industry. It's a shift that is fundamentally reshaping everything from global supply chains to basic manufacturing costs. We're talking about massive manufacturing and chemical plants making the radical decision to just completely abandon the traditional power grid. They are moving toward total operational independence. But, as you'll see, cutting that cord takes an extreme toll, specifically on the massive lithium-ion battery systems that make this whole thing possible. So let's dive into it.
Here's our roadmap for today. We'll start with escaping the power grid, then look at building the islanded microgrid, move on to the extreme engineering system challenges, dive inside the degrading battery, and finish up with the ultimate financial trade-off. If you're running a massive industrial operation today, there is really one urgent question that's probably keeping you up at night. How is your plant handling rising grid tariffs and reliability vulnerabilities? And let's be clear, this is absolutely not a hypothetical scenario. For energy-intensive plants, their entire bottom line, their global competitiveness, and their operational safety all hinge on exactly how they answer this single question.
Section 1. Escaping the power grid, the breaking point. Let's look at the inciting incident for this massive industrial shift. Heavy industrial plants are currently being squeezed mercilessly from two sides. On one hand, you've got skyrocketing grid connection fees that are making basic utility reliance incredibly, almost unsustainably expensive. And on the other hand, which is honestly arguably much worse, is the constant, looming threat of unpredictable brownouts. When you're running energy-intensive manufacturing, chemical processing, or smelting facilities, a sudden loss of power isn't just a minor inconvenience, it's downright catastrophic. Imagine a massive steel smelting facility operating at peak capacity. If the grid drops out unexpectedly, you don't just lose time, thousands of pounds of molten metal can literally solidify right inside the machinery. That single event can instantly ruin millions of dollars of highly specialized equipment and halt your production for months. This severe dual threat is exactly what's forcing heavy industries to fundamentally rethink their reliance on standard utility infrastructure. Dependency on the grid? It's out.
Section 2. Building the islanded microgrid, absolute autonomy. So if dependency is out, the new goal is absolute industrial autonomy. The path forward means shifting entirely from grid-tied dependency to a self-contained islanded microgrid. To pull this off, decentralized energy architects are combining three primary pillars: captive wind generation, extensive rooftop solar arrays, and heavy industrial battery energy storage systems, or BESS. When you link these three together, you create true operational resilience. You effectively become your own utility company. But to put this into perspective, we aren't talking about a couple of backup batteries sitting in a basement. No, we are talking about massive, warehouse-sized installations capable of powering a small city, entirely dedicated to running just one single manufacturing plant. And of course, taking on the role of a massive utility company brings some very heavy baggage.
Section 3. Extreme engineering system challenges, the industrial realities.
Cutting the cord to the main power grid introduces some highly complex, highly distinct engineering hurdles that operators now have to solve entirely on their own. The first major one involves inertia and frequency control. When you're tied to the main grid, that massive, interconnected national system acts as an unbreakable, stabilizing reference point. It dictates the frequency for you. But when you become an independent island, you completely lose that anchor. Without that massive central grid acting as a reference, industrial operators have to deploy what are known as grid-forming inverters. These inverters are absolutely crucial because they instantaneously establish their own voltage and frequency references. Essentially, without the grid, the plant has to artificially generate its own perfectly synchronized electrical heartbeat, pulsing exactly 60 times a second. Doing this seamlessly, without the massive safety net of the national grid there to absorb natural fluctuations, is an incredibly complex feat of continuous electrical engineering.
The second massive challenge is dealing with transient load steps. To understand this, think about what happens at home when a really powerful air conditioning unit kicks on and you see all the house lights dim for a split second, right? Now multiply that exact phenomenon by 1,000. We're dealing with massive induction motors and gigantic arc furnaces. When you turn these heavy industrial machines on, they require a tremendous, almost violent surge of startup current. In an isolated islanded microgrid, your local energy storage systems must be capable of supplying these massive shocks of current instantaneously. And the kicker? They have to do it without causing the whole system's voltage to sag and without triggering protective relays that would just shut the entire plant down. To handle those massive transient load steps, the local battery systems have to safely deliver extreme C-rate bursts. Now, a C-rate essentially measures how fast a battery is being discharged relative to its maximum theoretical capacity. In a normal, everyday consumer application, a battery might discharge gently over several hours at a very low C-rate. But here, delivering these massive bursts requires immense physical force and extreme electrical output from the batteries in just a fraction of a second. It is absolute electrical warfare on the internal components of the battery cell. The system is pushed to its absolute physical limits just to get the machinery spinning.
And finally, the third engineering hurdle, true black start execution. This is basically the ultimate high-wire act for an industrial plant. If a sudden, catastrophic fault actually does occur, and the entire islanded plant goes completely dark, the system needs a way to wake itself back up. True black start execution means the system has to flawlessly coordinate its local generation and its battery reserves to autonomously re-energize dead plant buses. Honestly, it's like trying to jumpstart a massive jet engine in mid-air. Every single breaker, inverter, and generator has to fire in the exact right sequence, perfectly timed to bring a completely dead industrial plant back to life with zero outside help. If even one step is off, the whole system faults out again.
Section 4. Inside the degrading battery, the micro-level stress.
Okay, so now that we understand the extreme heavy lifting these systems are doing, let's look inside the cells themselves. Because these batteries aren't just sitting idly waiting for an emergency. No way. They are actively subjected to high-frequency arbitrage cycles. This means the system is constantly buying or storing power when generation is high or prices are low, and then rapidly discharging it to run the plant when generation drops. The battery is working overtime all the time. Now combine those constant high-frequency arbitrage cycles with the extreme load demands we just talked about, like those massive violent C-rate bursts for machinery startups, and you get severe accelerated lithium-ion cell degradation. The chemical asset is literally wearing itself out from the inside, significantly reducing its operational lifespan.
So you might be wondering, how do plant operators actually manage this constant degradation to maintain thermal stability and preserve the asset's longevity? Well, the strategy has had to evolve drastically. On one hand, you have your basic threshold-based battery management system limits. These are simple, rigid rules that just shut the battery down if it gets too hot or is pushed too hard. It's safe for sure, but it's incredibly limiting. On the other side, the modern solution is predictive algorithmic dispatch. This acts as the intelligent brain of the operation. It constantly looks ahead, analyzing weather forecasts for solar output, upcoming production schedules, and real-time plant power demands to decide the precise, optimal moment to stress the battery. It dynamically balances the need for raw power against the absolute imperative of overall asset longevity.
Section 5. The ultimate financial trade-off, revenue versus degradation. All of these extreme engineering feats and complex software algorithms ultimately boil down to one brutal financial dilemma. It's a high-stakes balancing act of making money versus destroying your own equipment. On one hand, we have aggressive cycling revenue. When you cycle these batteries hard and frequently in an islanded microgrid, you generate immense operational savings and revenue. You completely avoid those skyrocketing grid tariffs, and you keep your production running flawlessly. But, on the other hand, this comes at the direct cost of accelerated capacity fade. The harder you work that massive battery system to maintain autonomy and make money, the faster you destroy the asset's overall lifespan. And when these warehouse-sized battery systems degrade, you are looking at bringing forward millions of dollars in replacement costs far earlier than anyone originally anticipated. The shift to islanded microgrids offers an incredible escape from rising grid fees and catastrophic brownouts, giving heavy industry the operational resilience it desperately needs to survive in today's modern landscape. But, as we've seen, it pushes lithium-ion storage to the absolute physical and chemical brink. So I leave you with this. When you weigh the incredible operational revenue and freedom against the harsh, expensive reality of capacity fade, is absolute industrial autonomy actually worth the accelerated battery death? Thank you so much for joining me for this explainer, and I hope this gave you a clear, structured view into the fascinating microgrid revolution.